tell us about blossoming trees and the scaling limits of simple maps.
Okay, first I'd like to thank the organizers. I've had a really nice time in Cambridge so far. And I'm going to talk about joint works with Lucia Darioberry, Olivier Bernardi, Gwendal Collet, Eric Fusy, and Dominique Pouallon. So also I should thank Gregory Mirmont for his talk, because this is going to save me a lot of time introducing some context. So a planar map is a proper embedding of a planar connected graph in the sphere. Here I'm just going to work in the sphere, and just for convenience, the planar maps are going to be rooted by pointing a corner, and I really want to consider planar maps as metric spaces where the distance is the graph distance between two vertices. Okay? And the family of maps we're going to consider today are the family of quadrangulations, where all the faces are quadrangles, the family of simple maps, so that are maps without loops nor multiple edges, and this is going to be one of the main objects, no loops. But we're also going to encounter simple triangulations and bipartite cubic maps. So bipartite cubic maps are maps where all the vertices have degree 3 and which are bipartite, that meaning that you have a proper two coloring of the vertices. Okay, so the first setting, the usual setting, is the setting of random quadrangulations. So you take the set of quadrangulations, as Gregory explained, you take the uniform measure on it, and then you view a quadrangulation, a random quadrangulation, as a random compact metric space. And the question is, how does it look like when n goes to infinity? Okay, so this simulation is due to Nicolas Curien, and it gives you kind of an approximation of what we call the Brownian map, what is limit of a uniform quadrangulation when we scale by n to the 1/4. I'm going a bit fast here because I think Gregory gave a really nice introduction to all these contexts. And the question I'm interested today is what the behavior, so that's, okay, sorry, I went a bit too fast actually. So what the behavior of Qn, so now we know that thanks to Schaeffer's bijection, which links quadrangulations and labeled trees, we can study the quadrangulations via these labeled trees, and it has been some ongoing works on the last 15 years to study what the limit is, what the typical behavior is. And again, I mean, there was the first work by Chassin and Schaeffer, and then some work by Marca Mokadem, Le Gall, Paulin, Mirmont, and which were concluded 2 years ago. 2 years ago, by the proof that normalized quadrangulations converge toward the Brownian map for the Gromov-Osdorf topology. Okay, so that's for quadrangulations. But the question is, what if quadrangulations are replaced by some other models of maps, like triangulations or simple maps, simple triangulations, general maps? We expect all these models of map to behave exactly in the same way in the limit. I mean, we expect the distance, the scaling to be of order n to the 1/4, and we expect the limiting object to be the Brownian map, no matter what the precise characterization of the discrete setting is. The thing is that quadrangulations are nicer to work with because we have this nice bijection due to Corey-Vauquelin-Schaeffer, but there is no reason why we should like quadrangulations better than other models of maps somehow. And so far, different models of maps have been studied. So quadrangulations were the first example. Then in the same paper, Le Gall proved that 2P angulations and triangulation also converge to the Brownian map. Then there is this paper by Beltran and Le Gall proving that quadrangulation with no pennant vertices. So pennant vertices are vertices which are of degree 1 somehow. And with Lucia Darioberry, we proved that simple triangulations and quadrangulations also converge to the Brownian map. And here you see that for simple, I mean, we forbid multiple edges and loops. Somehow we impose some constraint on the connectivity of the map, okay, which makes them somehow different to work. I mean, we can't apply this kind of bijection anymore. Then there was a result about general maps, and then for bipartite maps. Okay, and today I'm going to discuss simple maps. So, before moving further, let me state a really important remark. I mean, it took Grégory and Jean-François nearly, I mean, not only them, but it took people almost 15 years to derive the result of convergence toward the Brownian map for quadrangulations. And in 1 year and a half, you have all these results that appeared. It's not because people found another proof of this result, but really they use, I'm a bit dummy with it, okay. Really they use an argument by Le Gall in this paper that he actually used to prove the convergence of 2p angulations and triangulations to use the result for quadrangulations. Okay, I'm a bit imprecise here. Let me rephrase that. You have the model of convergence toward the Brownian map is really proved for the case of quadrangulations, and then using this result, we can somehow extend it to other models of maps, okay, by proving some results but not as strong as the one obtained for quadrangulations. Okay, so we really need the proof for quadrangulations first. Okay, and so somehow intuitively, if you look at the Schaeffer's bijection, the labels on the tree code the distance between a vertex and the root. So you have a good control of the distance between the vertices and the root, but you don't have so good control on the distance between any two other vertices. Okay, that's the thing that makes the limit complicated to understand somehow. Okay, but thanks to the result for quadrangulations, it's enough somehow now to prove that, and so to get convergence to the Brownian map. It's now enough so to understand the distance between a vertex, any vertex, and the root. And more precisely, we need to prove that this distance divided by n to the 1/4 converges to the Brownian snake that Grégory introduced in his talk. So that, for quadrangulation, was the result by Chassin and Schaeffer. Okay, so it's far from being enough to prove the convergence to the Brownian map itself. Okay, we need to understand to prove that the distance between 2 points is tight, and prove a variance under rerouting, meaning that the root of your map behaves like a uniform vertex of the map. Okay, and so if you have these 3 points, then you get, using Le Gall's argument, that your models of map converge to the Brownian map as well. Okay, and so to do that, I don't have. To do that, we're going to encode the map by some trees, study the limit of trees, and then try to relate distances in the maps by some function of the tree. I mean, it's always the same strategy. Basically, find some trees, study the trees, come back to the map. Okay, so let's see a little bit what kind of trees we can have, what kind of bijections between maps and trees we can have. So for quadrangulations, 2p angulations and triangulations, quadrangulation with no-permanent vertices and bipartite maps, we have this really nice bijection by Corey, Veclin, Schaeffer, and its generalization by Boutier, Di Francesco, Guiter, that Grégory described. So I'm not going to talk too much about that. The result by Bettinelli, Jacob, and Mirmont used a bijection with quadrangulations due to Ambion and Bird, which is really nice, but a bit somehow peculiar, not peculiar, a bit ad hoc to this setting. And the result I got with Luigi used bijection with blossoming trees. And the result I'm going today also use bijection with blossoming trees. So it's a different family of trees, somehow not with labels, but with blossoms. for which we can obtain new results. And these blossoming trees are really convenient when you want to somehow constrain the connectivity of the maps. Okay. They appear in a lot of these settings. So at this point, the natural question is, what's a blossoming tree? So a blossoming tree is a tree with some decorations, with some opening stems and closing stems, such that the number of opening stems and the number of closing stems are equal. Okay, so my opening stem are represented by these green outgoing arrows, and these closing stem by these blue ingoing arrows. Okay, if you have a blossoming tree and if you're a bit obsessed by maps, you can try to make a map out of it, and a natural way to do it is to try to match an opening stem with a closing stem. And I like turning clockwise. Okay, so I'm going to take an opening stem, and I'm going to look for the next closing stem in clockwise order on the tree, and I'm going to merge them together so as to create an edge. Okay, so let's do it again. A couple opening closing stem, we merge them, new edge. And I can iterate this process until I have no matched closing of opening stems. Okay, and because they are the same numbers, I can do that. Okay, so that gives me a way to starting from a blossoming tree to get a map. Okay. Obviously, this is by no means bijective, because if I give you a map, you take any spanning tree of this map, you add the opening stems and closing stem in a convenient in a compatible way, and it gives you a blossoming tree whose closure is a map. Okay, but wait a minute. So you can remark that here on my so-called closure edges, I kept the orientation. Okay, I kept a small arrow indicated that these edges were obtained by making some closures clockwise. Okay, so that gives me a partial orientation of my map. Now, if I start with a tree with an orientation, so I orient each edge of the tree, and I keep the same orientation of my closure edges, then that gives me an orientation of my map, of my full map now. Okay. So let me rephrase that. If I start from a tree with an orientation and I make the closure, what I get is an orientation of my map, and it's clear from the construction that the orientation you get here has no counterclockwise cycle, because my trees have no cycles, and because I make all the closure clockwise, the only cycle I can create are clockwise cycles. Okay. And let me make a brief cultural remark somehow, is that this is actually now a bijection. Let me be a bit more precise. If we have a plane map with an orientation without counterclockwise cycle, and with this accessibility condition I'm not going to discuss, then there exists a unique blossoming tree whose closure is this map. Okay, so that's a result initially by Bernardi, which I generalized a little bit with Dominique Poulalon. Okay, so in other words, if I give you this map with an orientation that is without counterclockwise cycle, and you can check here that from any circle vertex you have a directed path to the square vertex, then there is a unique way to open it as a blossoming tree. Okay. Okay, so now that was okay. So now what about simple maps? So let me remind a bit the setting. So we are going to consider the set of simple maps with n edges. Okay, it's a finite set. We can sample uniformly at random a map among this set, and we consider it as a metric space. So the set of vertices, and we have the distance, and forget about the 2 here, but we have the same scaling n to the 1/4 as we always have when we study maps. Okay. And seen as a metric space with the distance rescaled, this object converged for the Gromov-Hausdorff distance to the Brownian map in distribution. Okay, so I'm not going to define all this object because it was already done, so thanks again. So I want to, the rest of my talk is going to be devoted to the proof of this result somehow. So the first step is really to understand the distance between any vertex and the root. And to do that, I need to find some trees somewhere. from what I explained you about blossoming trees, I told you that it's a map with an orientation is the same as a blossoming tree. So if I want to find trees, I first need to find orientations. Okay. So we're going to do that. So first, I'm going to consider orientation for simple triangulations. So if I have a triangulation, applying Euler formula, we can see that the number of vertices minus 3 is equal to 3 times the number of edges minus 3 for a triangulation. Okay, so roughly there are 3 more edges than vertices. It somehow gives the idea that a good idea for an orientation would be to impose at each vertex as at degree 3. Okay. But if you have a vertex of degree 1, it's going to be quite hard to give this vertex of degree 3. Similarly, if you have a vertex of degree 2, it's going to be quite hard to give this vertex of degree 3. Okay, and these things could happen in a triangulation. Okay, this is a triangulation, and this is a triangulation. Okay, but you can observe that in these 2 drawings, I have either here a loop or here a multiple edge, a double edge. Okay, and in these 2 cases, I can't find a 3 orientation, obviously, because I have a vertex of degree 1 here and a vertex of degree 2. But if I forbid loops and multiple edge, then it's enough to get a 3 orientation of my triangulation. So let me state that a bit differently, maybe. If you have a triangulation, and if you can orient the edges such that each vertex has degree 3, out degree 3, then your triangulation has to be simple. And reciprocally, if you have a simple triangulation, you can find a way of orienting the edges such that each vertex has degree 3. Okay. I'm cheating a little bit. I'm saying each vertex because you have these minus 3 here and minus 3 here. You need to have a slightly different rule for the 3 vertices. I made 3 square vertices here, but I don't want to put too much attention onto that. Okay. So somehow, if you have a simple triangulation, you can always find an orientation of its edges such that each vertex has out degree 3. And moreover, there exists a unique way of doing that without counterclockwise cycles. Okay. Is that clear so far? Okay. So that's for simple triangulations. Now we need to talk about general simple maps. So in a simple map, a priori, you have less edges than in simple triangulations. So there's no way you're going to be able to have 3 orientations. You don't have enough edges to put all these outgoing edges somewhere. Okay. So what we're going to do there is, because we don't have enough edges to give each vertex out degree 3, we're just going to add some small buds like that, just to take care of this extra out degree. Okay. So now my orientation is prescribed to have out degree, still to have out degree 3 for each vertex, but even possibly with the help of these additional buds here. And I don't put these buds at any place. I have the constraint that each face of degree d has to be incident to exactly d minus 3 buds. So in this sense, it's really a generalization of 3 orientation for triangulations, because if all your faces have degree d, have degree 3, then they are all incident to 3 minus 3, 0 buds. So you have a proper 3 orientation in this case. Okay. And the same way that 3 orientation characterize simple triangulations, these orientation characterize simple outer triangular maps. So outer triangular means that the outer face here is a triangle. Again, it's a technical just make things easier. So, and this result is due to Bernardi and Fusy in 2010. So we have a characterization by these orientations, and moreover, we also have a result of uniqueness. So if we can always consider such an orientation without counterclockwise cycle, and let me erase that. So we have a 3 orientation with buds. So each vertex has our degree 3. And there is a unique orientation without counterclockwise cycles, and you have the additional assumption that each bud needs to be preceded by an outgoing edge. So it's just a local convention. Okay, so you start from a simple maps with an outer triangular face. Then you can always, there is a unique way to orient the edges of this map such that these 2 conditions here are satisfied. Okay, and if you can do that, then you know that your map is simple. Okay, so at this point, it would be really nice to be able to apply the results I mentioned earlier, saying that we then have a unique way of opening this orientation into a map, into a blossoming tree. Unfortunately, it's something we cannot do, or at least I don't know how to do it. It would be nice to know how to do it, mainly because we have these buds here, and we don't know really how to deal with them if we want to apply the generic results. So we need to do something else. Okay. Oh, yeah. And I would be useful to. So, sorry, I should have said that before, because you have exactly in each space of degree D, you have exactly D minus 3 buds. These buds somehow give you a way of triangulate in a canonical way the simple map. Okay. If you have a quadrangle, you need 1 additional edge to make 2 triangles, and so these buds can be used to do that. Okay, so now I'm going to describe the bijection we actually use to study the limit of simple maps. This is, I must mention that this is a reformulation of a bijection obtained earlier by Bernardi, École and Fusy, which I present here in a slightly different way just to make it easier for the analysis later on. Okay, so this may be not the most intuitive way, but it's the fastest way to introduce it. So let's do it. So we start from a rooted binary tree, and I have all my vertices have degree 3, all the inner vertices have degree 3, and I color in green the edges between an inner vertex and a leaf, like that. Now I'm going to orient each edge of the tree arbitrarily. Okay, and I'm going to split now each inner edge of my tree into 2 by adding a vertex in the middle and adding a blue edge on the right side of my edge. The right side means that if I walk along the orientation of my edge, I put a blue edge on my right. Okay, so I have a binary tree. Each edge is oriented, and I add a blue edge here. Okay. So now I can transform all the green edges into opening stems and all the blue edges into closing stems. Okay. And I make the closure of this tree. Okay. Because in a binary tree, if you have n edges, you have n plus 3 leaves. At the end of the construction, you have n plus 3 opening stems are actually going to remain unmatched. Okay. In my drawing here, one of them is incident to the root. It means that my tree is balanced. It's just technical assumption. And these 3 stems, I'm just going to take care of them by saying that I'm closing them to infinity. Okay, so I get a map. This map is cubic. Each vertex has degree 3. The vertex in the tree had degree 3 at the beginning. And the vertex I inserted, and the vertices I inserted in the construction at degree 2 in the map, and receive exactly one closure edge that comes from this closing stem I inserted. Okay, so everybody has degree 3, and this map is bipartite. You can see it from the construction that all the closure edge go from a black vertex to a green vertex. Okay, and this is actually a bijection to Mireille Bousquet-Melou and Gilles Schaeffer between balanced oriented binary trees and bipartite cubic maps. Okay, so that's the first step of the construction. Now, to give you the second step of the construction, I'm going now to use labels. So I start with the same object, my oriented binary tree. I have opening stems and closing stems. And I'm going to label the corner of this tree as follows. So I start with at 0. And each time I see a closing stem, I increase by 1. And each time I see an opening stem, I increase by 1. And each time I see a closing stem, I decrease by 1. So here I have +1, nothing happens, -1, +1, again nothing happens, +1, etc., etc. And that gives me a labeling of all the corners of my tree. Okay. And I really want to emphasize that these labels, I mean, so far have nothing to do with any distances. Okay, they're just somehow they give you the depth of a face in the closure of this tree. If I look at this vertex, at this label 3 here, it means that it's going to be wrapped by 3 closure edges in the bipartite cubic map in the end. Okay. In a way, you can see it as a distance maybe in the dual graph, but even that is not completely clear. Okay, so, but we have this label. So, because we have really a lot of steps in this bijection, I should recall them here maybe. So, that's the root of my tree. Let's say I have an edge oriented like that. So in this case, if my label is I here, my label is going to be I -1 here, because it means that I have a closing stem here. And if my edge is oriented in the other direction, it means that the blue edge is here. So if I have label I here, nothing happens, so I keep still I have label I here. And if, for example, I have an opening stem here, it means that I will have label I +1 here. Just a small recap of the rules I used to label my tree. Okay, so now, and the 3 unmatched stems I had before are exactly the last corners labeled respectively 0, 1, and 2. Okay. So now, what I'm going to do is to use these labels to insert new opening stems. Okay, and the way we're doing that is we're going to add a purple opening stem before each descent in my labeling of corners. Okay, so if I have so again, the root of my tree is always on the top of the board. I'm sorry about that. So if I have label I and then label I -1, I'm going to insert a purple opening stem. Okay? I do that for each corner, and then I erase everything which is non-purple. I get rid of the blue, green, everything. And now I'm left with some opening stems with labels, and I do the closure in the following way. If I have an opening stem labeled I, then I'm going to turn around my tree in clockwise order and until the next label I-1, and then I'm going to close this opening stem just in this corner. So in this way, this is reminiscent of Schaeffer's bijection, where you go from label I to label I-1, but the way it's constructed somehow it's kind of different. Okay, so let's do that. So here I have my purple stem labeled 3. I'm going to walk around my tree, find this label 2 here, and I'm going to close it here. Okay, another example, this purple stem here 4. I'm going to walk around my tree. Here it's 4, so it's not good. I'm going further. I'm finding this 3, and I'm closing it here. Okay, so that's the way the labels are constructed. So really, you have to wait for the next corner with label I-1, but which is also a purple corner somehow, because I erased everything which was not purple. Okay, so we do that for everybody. And at the end of the construction, some stems again remains unmatched. This is because I have these, what I said a bit earlier about the stems that remain unmatched in the cubic map. Somehow, after this first ray, infinite ray here, I know that I have no labels less than 1. So all these stems labeled 1 are going to be unmatched in the end. And here it's the same after this infinite ray here. I know that I don't have any labels less than 2, so all these stems here are going to remain unmatched. To end the construction, I add 3 vertices in each of these sectors, and I connect the unmatched stem to each vertex in each sector. I mean, this is really some detail. You don't really need to get that, but we can finish the construction somehow. And to really finish it, then we make a triangle out of these 3 vertices. Okay, so that's what the bijection. So it's there is a lot of steps. So let me maybe summarize here what I just did. So we start with a oriented binary tree. From the orientation, we construct a blossoming tree. Thanks to these 2 rules, thanks to this rule. That gives me some labels on my tree. And thanks to these labels, I insert, can you see here actually? In the back. Insert purple stems before it descends. Okay, that's how the bijection goes. Okay. And this is a bijection between outer triangular simple maps and bipartite cubic maps. So at this point, I don't really wish to, I don't really hope actually to convince you that this is a bijection. The only thing I can maybe do is try to convince you that what we get is a simple map. I mean, there is no reason why we don't create loops or multiple edges by doing this construction. And the proof that this is a simple map is going to rely on the characterization by simple maps with this kind of orientations. Okay, so that's where orientations actually play a major role. So if you remember, we started with this with this oriented binary tree, and we had this rule to insert purple opening stem. Okay. Each inner vertex of the tree is incident to exactly 3 other vertices. So it can get either 0, 1, or 2 or 3 purple stem. Okay, you get at most 1 purple stem per corner. Okay, if you get 0, then you're going to disappear in the map. So let's not worry about these guys. If they get 3, that's perfect. They have our degree 3. We're fine. Now, if they get 1 or 2, for example, this guy here got 2 purple opening stems, or this guy got 1, then we're just going to add additional pink stems. I don't know if you can tell the difference between pink and purple, but some pink stems in the remaining corners. Okay, so now everybody has our degree 3. Okay, we're going to do exactly the same construction. I'm not going to redo it, just without worrying about these pink opening stems. Okay, we just ignore them. Okay, we get a map. Now the good thing with the map is that every vertex now has our degree 3. I mean, that's where we started from. Okay, and if you believe me, you can see that what you obtain in the end is a map. The orientation has no counterclockwise cycle. Same thing, because we make all the closures clockwise. Every face of degree D is exactly incident to D minus 3 pink opening stems. Okay, and plus, because of the way we define everything, we also have that this local rule is respected on this construction. I mean, it's really from the construction. It comes directly from the construction, and you can, I hope, check it on this example. Here I have a pink stem, and I can see that just before my edge is oriented outwards. Okay, so what I get really when I do this bijection is an outer triangular simple maps endowed with this kind of orientation. So at least I know that this is a simple map. Then it remains to prove that it's a bijection. Okay. So, and if we take the two bijections together, that gives us a bijection between outer triangular simple maps and balanced oriented binary trees. So we found our trees. Okay, so now we need to find how we can control the distance in the map as a function of these trees. Okay, so the good thing about these trees is that they get labels. So what would be nice is that if these labels would actually encode some distances, okay, which is not clear at all from the construction. But before they do encode some distances. Before explaining how we can see that, I'm going to just have a look at these trees and see if we can study the limits and see if these trees as labeled trees converge to the Brownian snake. So that would be one part done. So just to simplify a little bit the setting, I'm going to, for each kind of tree like that, I'm just going to erase all the blue and green buds and replace the labels around the corner by just the minimum of them. Okay, so here I keep label 0, so it's not really interesting in this setting, but. And so I obtain a really simple tree. I mean, it's just a binary tree with some labels, and the labels along the edges differ by 0, -1, or +1. I can look a bit closer what's going on. From the construction, I know that the labels around a corner are going to behave like I-1i and then I+1. And for instance, if I list all the possibility for a node of degree 1 in my original tree, you have 4 configurations depending on either whether this edge is oriented inward, this vertex, or outward, and depending of this opening stem is on the right side or on the left side. And you have to write down all the possibilities, and that gives you somehow the distribution of how the labels behave along the tree. Okay, it just takes 10 minutes. So if you summarize, I mean, if you do the analysis of for vertex of degree 1 and for vertex of degree 2, you obtain that the trees with labels can be seen as Galton-Watson trees with some random displacements on edges following this law. I mean, if you have a vertex of degree 1, then you have this distribution, and if you have a vertex of degree 2, you have this distribution. So this is a fairly standard setting. The only thing which is a bit annoying here to prove the convergence of the Brownian snake is that you can see that the left child always get a label which is less than the right child. And usually we like things to be identically distributed among children, which is not the case here, but fortunately this case was carried out by Marker in 2008, where he obtained that these models of tree converge to the Brownian snake when the labels are normalized by 2n to the 1/4. Okay, so this is just this result. You have the control process and the label process. Gregory explained that. So the control is just the walk, when you walk along the tree and recording the height. And if you record the labels as well, you converge. You get convergence to the Brownian snake when you rescale the contour by n square root of n and the labels by n to the 1/4. Okay, I'm going to skip this part because I think that's fine for everybody. Okay, so these trees, we understand them well. Okay, so why are they important? Why these labels? How can we code some distance in the map as some function of the labels in these trees? Okay. So the first claim is that the label in the tree is going to give an upper bound of the distance to the root in the map. So why is that? You can remember from the construction that the way we constructed the map was to say I'm going to start from I'm going to start from a, let's say, purple corner labeled I, and I'm going to create an edge going to the next purple corner labeled I minus 1. But because here I have a corner labeled I minus 1, it means that here I have an opening stem. Okay, and this one I'm going to close it at a purple corner labeled I minus 2. Okay, and if I just follow this path, meaning that somehow I take the leftmost path, I mean here I arrive here and I take the first left I can take, the labels along this path decrease exactly by 1. Okay, and eventually this path is going to reach the outer face. This is because, so this is a leftmost path. So why is it going to reach the outer face? I mean, this path cannot loop in that direction because we say that there is no counterclockwise cycle in our orientation. So this is impossible. It could be the case that this path, loop in the other directions, but that cannot happen, and I'll explain a bit why later, but it doesn't happen either. So they don't loop, so at some point they had to reach the outer face. So if I follow such a path, this path has length exactly I, it goes to the root vertex, so it gives me an upper bound on the distance from a vertex to the root. Okay, so here is an illustration of what I just said. So now actually leftmost paths are much better than that. They are not just approximate, just don't give an upper bound, they actually almost geodesic path. And why is that? So I have here my leftmost path in red, and I have another path in my map, and I ask whether this blue path can be shorter. And now I'm going to consider, so my map here is endowed with its tree orientation. I'm going to add the buds. And because of this local rule here, you can see that if I'm following a leftmost path, if I have some buds at this vertex, then these buds have to be on the right side of the path, because otherwise, if I had, let's say, a bud here, by my local rule it means that I have an outgoing edge here, and now this is not a leftmost path anymore because this would have been the leftmost path. So I can somehow add the buds, and this purple path remains a leftmost path. Okay. So that's what I'm doing here, and I can consider now the submaps, which is enclosed by the. So I have my. That's not enough boards actually. Okay, let's go on the other boards. So I have my leftmost path in red. Maybe the blue path starts the same way. At some point it left, and at some point it comes back to the other path. I mean, and they eventually meet. I mean, they can meet at the root vertex maybe, but they meet at some point. And so I can consider what's going on in this part of the submap. It's a submap, okay? I can use the buds of my orientation to triangulate this part of the submap. So now what I have inside here is a simple triangulation with an orientation, okay, and with a boundary. And now I can apply Euler formula that gives me a link between the number of edges and the number of vertices and the length of this submap. And I also know that I have a 3 orientation of this submap, so that gives me also a link between the number of edges and the number of vertices. Okay. And if I combine these two inequalities, it gives me that the length of this leftmost path has to be, the length of the other path has to be longer than the length of the leftmost path. Okay, it's just a counting argument. I mean, you just write Euler formula, you just write the fact that you have algebraic 3 per vertex, and that gives you the result. Okay, so it seems perfect. In fact, that's just one possible case. So here in my blue path, you have 3 other configurations that can happen. Your blue path can leave on the left and come back from the left, or it can actually wrap the vertex you're starting from in one of these 2 directions. You do exactly the same. You do Euler formula, but now because this guy here is the leftmost path, the counting is going to be a bit different. Okay, and in these 2 cases, everything works really fine. But in this case, what you can get is actually that this blue path is slightly shorter than the red one. Not by much, but it can. Such a wrapping somehow can improve the speed by 2. I mean, you can be 2 edges shorter. Okay. So, but the good thing about it is that it cannot happen too often. So so don't look at this drawing because I think it's really misleading actually. So I'm going to make another one. So you have your vertex U is here, and the root vertex, let's say, is here, and your leftmost path. I mean, because it's leftmost, I'm going to make it turn for me. I'm not saying it behaves like that, but and I have the other path. The other path may start at the same. That's complicated. Other path start here, and for it to be a shortest path, I need to make it go like that. Yep. So it has to, sorry about that, it has to start to leave on the right and come. Okay. I can't, I'm confused with my choice of colors. Yeah, it has to leave on the right and come back from the left. See. Leave from the right, comes back from the left. Leave from the right, comes back on the left. Leave, okay, something like that. Okay. And so if you have that, for example, this guy here may be shorter than this part here, but not much shorter, only by 2. Okay. So what could be a bad case scenario? we know that this red thing here has length of around n to the 1/4, because we know that the label of the tree, when rescaled by n to the 1/4, converges to the Brownian snake, say. It's approximately n to the 1/4. If we want this blue thing to be really shorter than that, okay, because at each of these wrapping, we can win at most 2. We need a number of wrappings to be comparable with n to the 1/4, because we scale everything by n to the 1/4, so everything or bigger to the 1/4, okay? Because it's 2 at each time, so if it's less than that, you're not going to see it in the limit, okay? But you also need that the sum of the lengths of the wrappings have to be big O of n to the 1/4, because I mean the length of the blue path is more than the sum of the length of the wrappings, and you want this guy to be shorter than the red path, and the red path is of order n to the 1/4. Okay? So you have a sum of n to the 1/4 element, and this sum should be of big O of n to the 1/4. So it means that a huge majority of these wrappings then, or at least one of them actually, with constant length. Okay. You want many wrappings, but you want that the sum of the length of all of them is rather short. So if they're all long, it's not going to happen. Okay, so one of them needs to be short. And if I take like one in the middle, it means that I have maybe no, not helping. Okay, it means that at some point in my map, I have, let's say that these. So let's say that this wrapping here is the one with constant size. Then this red thing has also a constant size plus 2 at most. So it means that this is a cycle with constant size. Okay. And inside it, you have a huge proportion of the map, and not a huge, but a macroscopic proportion of the map, and outside it as well. And so your map somehow is strangled by this wrapping, this circle which has to be short, separating the map into 2 macroscopic proportions. And we know that this can't happen. Okay, your map somehow you can't have something like that in your map, where here you have a macroscopic proportion of vertices here as well, and here a small circle. Okay, so gathering all these unwavering arguments, we get this statement that say that if the bad event, that there exists a vertex such that the label is much more than the distance to the root, then the probability of a bad event goes to 0 as n goes to infinity. Meaning that these labels somehow really encode some distance in the tree in the end, in the map in the end. Okay, so that was the first item I erased. So that's proved now. To prove that the distances are tight, that's a really standard argument. We can remember this construction here, going from a corner label I to a corner label I minus 1. So if we have two vertices, u and v, with label zu and zv, then we can take the minimum. I mean, Gregory explained that in the case of quadrangulations, but it's exactly the same kind of argument here. We take the minimum of this label between us two, and we know that there is going to be a path from u to this vertex of length zu minus check z, and we can do the same construction here from zv, and combining these two paths gives us a path from u to v whose length is bounded by this quantity. We know that this converges, so it gives us that this distance is our tight. I mean, there's really nothing new. I mean, there's exactly the same argument appears for quadrangulations. Okay, and that's a description of the Brownian map, but I think you had that before. Okay, so I guess what I really want to emphasize is how we somehow starting from these blossoming trees where you have a priori no notions of distances, we can actually control some distances. And it's nice to see that what we introduced with Luigi, with this leftmost path, actually work for simple maps. I mean, it's much more involved. I mean, we have to use this really nice bijection that Gwendal, Eric, and Olivier introduced and reinterpret it so as to make everything work. And the natural further steps, somehow I present you at the very beginning of this talk, this idea that if you have a blossoming map with an orientation, you have automatically somehow a family of blossoming trees. So that's a joint work with Dominique Poulalon. But Olivier and Eric has also a really nice setting where they somehow gathered a lot of families of bijections under a somehow generic setting. And it would be really nice to see if we can do something like that a bit more generically. I mean, not to do each family of maps one by one. And so far, this is something, unfortunately, that we cannot do. And somehow, if you want to summarize that with potato diagram, we have this generic scheme for bijections, which includes a lot of families, natural families of map, Eulerian map, non-separable cubic maps, simple triangulations, and here are the families of maps where we know bijection with blossoming trees, where we can control the distance via leftmost path, but which are not somehow, so far, particular case of this generic scheme here. So that's really something we should try to understand better. And I hope that I actually convinced you that the leading role here is played by orientations and that they are really nice. And thank you.
Are there any questions for Marie?
You don't have to.
This will go one more question. Slightly off topic. We expect to find suitable bijection of blossoming trees and simple planar graphs instead of maps.
No. The thing is, with simple planar graphs, I mean, in maps you really have this embedding, meaning that you have somehow a canonical ordering of the vertices around, canonical ordering of the neighbors around one vertex. Okay, and when you have a blossoming tree, I mean, this ordering is somehow inherent from the construction. Mm-hmm. Okay, what we could do though is to find, I mean, you probably know that. So graphs don't have an embedding, but if you go to three connected graphs, they do have a unique embedding in the map. So three connected maps and three connected graphs are the same. For three connected maps, there exists bijection with blossoming trees. So, and I tried to do this kind of stuff. So far, I have a way to do it somehow, but via irreducible triangulations. But for three connected graphs only. Okay.
That'd be possible. Okay.
I think for general graphs, it's somehow inherent from the construction that blossoming trees are not going to be the relevant tool because you have this embedding that comes with the bijection, really.
So you still have to go from three, even if you manage three connected, you still have to go from three connected to two connected, which is rather involved.
Yeah, but that's definitely something I'm trying to do.
Okay.
Any other questions for Marie? So if not, let's take a look at that.